Greetings, class. This is Dr. Royer. This is session 2 for business finance, and I wanted to kind of go over the things in the assignment folder for you, and then I'm going to cover what's in the text like I did last time. I apologize for the delay, but we've had a death in the family, and it's caused a little bit of a change in the schedule, but next week we'll be on track again with the usual. But anyway, this video will cover the discussion that we're going to do. And this week you'll notice the discussion is all about assuming you were receiving a large inheritance from a rich uncle, and you basically are going to have the option. You can choose either a lump sum one-time payment of $2 million or a series of 20 annual payments of $165,000 that cannot be transferred to another person upon your death if you were to die before the 20 years expired. So which would you choose and why? There's not a right or wrong answer to this. You can choose either one, and you can decide why you might do that. Basically, the decision-making process in a case like this is really a question of future value and present value and what you want to do with that money, and how you want to receive that. So this question, by the way, while it seems pretty far-fetched maybe to most of us, it's not necessarily unrealistic, and there are things like this that do occur. So you may want to give it some thought. Certainly that is basically the content in this session that we're going to talk about. Then we have some Chapter 2 problems that I'll talk about later as we go through the chapters. And then finally we have the learning activity in session 2 that's going to be a response to an article that discusses even principal payments and even total payments, and basically how those are working and how they work. And what you're supposed to do here is read through the article and then look at these 5 questions and respond to them. And the article is going to describe how those 2 different functions work and what they are, and you're going to understand what those mean and how they function. And you need to write responses to these 5 questions. So you're going to look at those, the way they work, the advantages and disadvantages, and describe a situation that might work best for each kind. And then explain an actual situation that you're aware of where a business or organization needs to borrow money, and make a recommendation as to what type of loan they should actually pursue. And then be sure to present your arguments and any supporting that support your recommendation. Now, according to the instructions here, you want to spend some time reading and studying about the 2 types of loans, and do any additional research necessary on these 2 types of payment schedules. Write a 3-page paper in Microsoft Word and format it according to the APA standards. And then you want to upload that into the assignment Dropbox. Now in this case, what you're going to do by formatting it APA, you want to use a title page, you want to use a running header, running head, and then basically remember that for APA the title page running head includes the words running head, but not on subsequent pages. And then you also want to include page numbers and all the other formatting characteristics related to APA. If you have any questions about any of that, please let me know. But for right now, I want to go on to the content that's included in these 3 chapters, and then I'll come back and talk about these problems at the end of each chapter. To start with, we want to look at Chapter 4, and this one is an introduction to the time value of money, and we're talking about present and future value concepts. Many of us are aware of what happens when you save money in a savings account and it grows over a period of time, and we are aware of the way that works. But with this concept, with the concept that we have, we're looking at some of those examples like what the discussion prompt asks you about. What if you were to receive a lump sum value of money? Which would you rather have, the lump sum value or the total of these payments? And here we have a case where they talk about that. Does this mean the winning ticket was worth $110 million? The answer is no, because the jackpot is going to pay out over a 20-year period at a rate of $5.5 million a year. That doesn't mean you're going to get $110 million when you get the jackpot. It means you're going to get, it's still a lot of money, believe me, but you're going to receive this over a period of time. It's not a lump sum, as many people might imagine. So the time value of money considers how we receive that money or how we invest that money. So when we start thinking about investing and putting a certain amount of money in an account and investing for a period of time, we think of taking a lump sum of money, putting it in an account, and seeing what it'll grow to over the next however many years. Well, if we're investing for a single period of time, it's fairly simple. We just take that money and multiply it times the interest rate. And the example here is $100 at 10%. Well, at the end of the first year, we have $110 because we've earned $10 interest at 10%. But when we start going over longer periods of time, the matter is complicated a little bit because we begin to earn interest on interest. In other words, the first year they pay interest, we get $10. The second year, we have an investment of $110 that they're going to pay 10% interest on. Part of that interest is interest on the interest we've already earned, so we need to compound that. It continues over an extended period of time. So that's what we're really talking about. Now, the process of leaving money in an account and letting it accumulate interest is called compounding because you're earning interest on interest, which is compound interest. Simple interest, they only pay you a certain amount of money on the face value each year. They don't consider the compounding of interest. But this is a very important concept, and it really can illustrate or can be used to illustrate how money can grow rather rapidly if invested and left in a particular investment for an extended period of time, and none of it is drawn out. So when we look at this, we can compound it by saying, okay, in the first year we take 110 times 1.1%, or 1.1, which is 1 plus 10%. That means that we get $10. In the next year, we're going to take that $110 and we're going to multiply it again and again and again, and that will give us a compounded amount of $121 over a period of time. Now, what they're doing in this calculation here, and they don't really explain it very well, is in the first year you earn $100. And you take $100 and you earn $10, and so you have this 1.1% or 1.1 factor for interest, 1 plus the interest rate of 0.10. Now you can calculate over a period of time what they call a future value factor, and that's going to take these interest rates, this interest rate, and you're going to increase it to an exponent of how many periods it's going to be invested. So if we go down here to the formula, the future value formula, if any amount we invest, $1, a lump sum, whatever, it's going to be 1 plus the interest rate raised to the power of how many periods we have it invested. So if you want it invested for 2 years, this would be to the power of 2. If you want to invest it for 3, the power of 3, and so on. In this case here, it looks like we're talking about 3 years. So instead of 2 years, it would be raised to the power of 3. So after 3 years, we would see $133.10 in the account. After 1 year, it's 110. After 2 years, it's 121. After 3, it's 133. Now, the way we get there is we take, and they're showing the longhand math here, but we're really taking the number 1 plus the interest rate, 0.10, that all together and raising that to the exponent of how many periods we're going to have it invested. In shorthand for finance, we can abbreviate it here. This is the future value, FV, future value of an amount that's invested and the rate and the length of time are the number of periods. The future value factor that we're talking about here may be computed as they do here. You see what they're doing? They take that and they say, okay, we're going to take the interest rate plus 1 and we're going to raise it to the exponent of 5 because we want it invested for 5 years. That's the same thing as saying 1.1 to the 5th power, which is 1.6105. That is the future value factor. You can get tables that have those factors already in them, but it's a good idea to know how to compute them. So what you do is you take that factor then times the amount that you're actually investing to show what that future value is going to be worth. So the growth of this $100 is illustrated if we go down here in table 4.1, and you can go through and compute this out as you want, but it shows the same thing as if we use the future value factor up here. You can compute it out. It's a lot more work, but if you know how to use a future value factor, you can just compute it in one nice step, and you don't have to go through all the 5 years of computations. Basically, interest growth is a function of time and rate. So the longer it's in, the higher it grows. The higher the interest rate, the higher it grows. So it's a combination of those two things. Here is a graph that shows you the effect of a change in the interest rate. If you have invested at 5% compared to 15%, you see that by year 10, 15%, you have a much higher increase in the future value of that money. And that makes sense because the longer it's in, the more the interest it's paid, the quicker it will grow. So here's a table with all the future value interest factors at 5, 10, 15, and 20%. Now this is nice, but many times you don't deal with interest rates at these 5, 10, 15, and 20%. Maybe there's an interest rate at 6% or 7% or 12%. So it pays to know how to compute that future value factor. But basically, if you're using a table, you look at the amount of periods that you're going to invest for and the rate that you're going to invest at. So if I want to invest at 5 years at 15%, my future value factor is 2.0114. I multiply that factor times the amount of money I'm investing to understand how much money I will have at the end of 5 years. So I think we've talked about the compounding interest and how it works. Basically, I want to get down here to the financial calculator. They talk about this here, and with your financial calculator, depending on the brand, there may be some different arrangement of the keys. I don't know. But typically you have these keys that relate to what we're doing here. We have PV for present value, FV for future value, PMT is payment, I/Y is the interest rate per year, or the interest rate per period, and then N refers to the number of periods that it's going to be invested at. So we have interest rate, number of periods, payment, present value, future value. So typically they show you how to do this if you're going to actually calculate this. Now again, I want to have a word of caution here. Your individual financial calculator may or may not follow these exact steps. If you have a question about that, you should look at the book that came with your financial calculator or the instructions, just to make sure you're following those according to what the manufacturer says. Now, one of the things that we do with present value and future value is we figure out with using present value, it's going to be the opposite of future value. In that last section, we were really interested in what the amount will grow to become. Now what we're looking at is if somebody offers me an investment today that will return a certain amount in the future, I need to know how much I should actually pay for that. So let's say, for example, somebody is saying, okay, I'm going to give you an investment and it will return X amount of dollars in the future or at a certain percentage rate. What I can do then with the present value factor is actually compute that and see if they're overcharging me or not for that investment. So here, for example, when we were looking at future value, we said 1 plus the interest rate raised to whatever power we're using for the number of periods that we're investing in. Now with present value, we're going to do that inverse of that, where we actually take 1 over 1 plus the interest rate raised to that power. So when we take our investment, we're going to say the present value of $1, whatever we're investing for a given period of time, for 1 year at 10%. If I were to say, okay, I'm going to invest $1 for 1 year at 10%, what is it worth now? Well, if I do the calculation, $1 divided by 1 plus the interest rate, I don't have to use an exponent because it's only for one period. I get an amount of 90 cents, well actually 0.909 cents for that dollar. That means that if I put 90.9 cents into the bank today, in a year it will grow to $1. When we say discount, what we're looking at is saying we know what the future value of this is going to be. What is it really worth right now? So that's what present value looks at. Future value, on the other hand, looks at if I invest a fixed amount today, what will it grow to be in the future? So in that way, present value and future value are opposite in their relationship to each other. Present value is interested in what is the value right now, or what should I pay for this. Future value is interested in what will it grow to become. So here's an example. We need to know the present value of $800 in 1 year at 7%. That's the interest rate. So what we do is we say the present value times 1.07 is going to equal $800. That's the future value of this. Well, we know what the future value is. But in order to get to the present value, we can't use it. We're going to look at this computation. We're going to have to rearrange it because we will not be able to get there with this unless we do some mathematical changes. So when we rearrange this in order to solve for the missing value, the present value, we're going to take $800, which is the amount that it will grow to in 1 year. That's the future value. Multiply that by 1 divided by 1 plus the interest rate. And this whole thing would be raised to an exponent if it were more than 1 year, but it's not. Since it's 1 year, the exponent 1 returns the same value. We don't have to worry about that. So we take 800 times 1 divided by 1.07 and we get $747.66. What that means is if we are promised $800 in a year, we should be willing to put $747.66 if we want to earn 7% interest in the bank. That's the right amount. You may have some investing folks who aren't that clear about that up front, so you need to be able to check out what they're telling you to make sure it's correct. So again, in this case, you have the $747.66. You put it in the bank for a year at 7% interest. You're going to have $800 at the end of that first year. So the present value formula is going to look like this. We'll take $1, which is the amount of the future value. That's what we want to have in the future, times 1 divided by 1 plus the interest rate. And that would be raised to whatever exponent for the number of years that we have it there. In this case, it's 1, so it's not going to make any difference. In other words, the present value is the $1, the lump sum in the future, divided by 1 plus the interest rate. Now, if we have more than one period, that's where the exponent is going to come into play. The formula itself doesn't really change anything. or doesn't really change, but we do use exponents with it. So now here's a question. It says, now let's say you have an amount invested that must grow to $1,000 over the next 2 years. So here we want to know how much do we have to have in there to get that 1,000 in 2 years. So we could do this calculation that says 1,000 is going to be the present value, and then that's what we're actually going to do is we're going to grow that to $1,000, but we're going to have this interest rate of 0.07 or 1.07. So we're going to take the present value times 1.07 times 1.07. That's 2 periods. The other way that we could say this is to take the 1.07 and raise it to the second power, which is what they do here. When we put 1.07 with an exponent of 2, we get a present value factor of 1.1449. So we know that we want $1,000 in 2 years, so we take that $1,000 in 2 years divided by the present value factor of 1.1449 will give us $873.44. That's the amount that we need to invest in order to achieve our goal if the interest rate is 7%. So, I hope this makes sense. Now here's a good question. You'd like to buy a new automobile. You have $50,000 in savings, but the car costs $68,500. If you can earn 9% interest rate, how much will you have to invest today to buy the car in 2 years? Do you already have enough? And assume that the price will stay the same for the car. So what do you need to know? Well, we want to know what the present value of $68,500 is today. In other words, that's our targeted goal. That's what we want to have. So we say the present value of $68,500 divided by 1 plus the interest rate, which is 1.09, all of that raised to the second power, the exponent, in order to figure out what that, and that will be our present value factor once we compute this. In other words, 68,500 divided by a present value factor of 1.1881, which means we should have $57,655.08 right now in the bank if we want to have it grow to the 68,500 in 2 years. So we're short on cash, even if we're willing to wait 2 years. Here at 4.2, they show you the summary of the present value formula. This formula is one that will be used over and over again. This is a present value of a lump sum. So when we're looking at this present value, what we're looking at is taking a lump sum amount, which is a future amount that we don't have yet, and deciding if at the rate we can earn, if we can actually accumulate that in a certain period of time. We may also say, okay, what will we have, or what is it worth now? We don't know what the present value of it is, but if we say in the future we're going to have, for example, in this case, 68.5 in 2 years, what is the present value of that? Well, the present value is 57,655.08. All that means is to invest at this rate and to get to this amount, we need to have this 57,655.08. So all of these computations are based on really the importance of a couple of things. One is the length of time it's invested, and the second one is the interest rate. So when we're talking about discounted cash flows, we're talking about the idea that, okay, we may have a promised payment in the future, but what do we actually have now, or what can we get out of it now? So let's say you see these advertisements on TV. I want to know, or I want to get my cash now from a structured settlement. Well, this is what they're doing. In those structured settlements, what they're doing is they're saying, what is your structured settlement now? What is the current interest rate? And given the length of time that you have to wait for this payment to come, how much is it worth at the present time? And so they discount that amount. So for example, in this case they're talking about investing $657.50 to have $1,000 after 3 years, but it could equally be what will somebody pay you for that, and they're going to discount that based on how far in the future it is. Now, when we're talking about actual present value factors, this factor is 1 divided by whatever the future value factor is. So you see 1 divided by 1.5209. That's 1 divided by that to give you the present value factor of 0.6575. That's the present value factor. Now the big thing to notice here, like I said, present value, future value are opposites of each other, but also that this 0.675 or 6575 compared to future value factors is less than 1. In almost every case, future value factors are going to be higher than present value factors. Present value factors will seldom be over 1. It is possible for that to happen, but it doesn't happen very often. As you can see from this table here, all of these are less than 1. That's not a hard and fast rule, but it is one that's a good guide. Now, if you're using a calculator to do present and future value, they give you this information here. And again, when you're doing calculator type problems, the names for the keys and how they're arranged are different, perhaps on different models. But you can follow these instructions in general to get have an idea of how to compute that. Now, here's one of the things to think about. When you're using this and when you're using Excel to calculate present and future values, you'll get a negative sign here for the present value, a negative amount. That's because in financial calculator terms, this is considered an outflow or a payment. It's not something you're receiving. It's going out to somebody else. Okay, so that's really that amount that are dealing with present value. You'll see with present value, the longer the time, the higher the rate, the deeper the discount, mainly because the rate times the time it's invested are the biggest factors in how much interest will be earned. So the more interest is earned, the less principal you need to invest, or the less that it's worth right now. Anyway, that's really that for that one. Now, when we look at present value factors, we may at different times want to figure out different things about them. We want to figure out whether an investment's a good investment or not. And so they talk about this here, evaluating an investment. You can do that with present and future values. And in this case, the example they give us is really not a good investment. They're telling us, okay, well, we probably wouldn't want to do that. And that's how you can use these computations to figure that out. A discount rate, like I said before, you take in terms of that we've been talking in present value and future value. The present value of any amount is the future value of that amount divided by 1 plus the rate. And both the present value and the rate is going to be raised to the power of whatever period that is. So here we have a question of finding a rate for a single period investment. You can use the present and future value formulas to find rates and basically find the time that's required to grow that investment to a certain amount. It's really mathematical, and it's just a matter of using certain pieces of information you may have, leaving if you're looking for the rate will be blank. In this case, they solve for the rate and they get 8%. You may be solving for time. And if that's the case, basically you'll do the same thing. You'll just leave the amount of time blank and you'll be looking for, or use it as a variable, and you'll be looking for that. You can also, again, go back to your financial calculator and use it, and you may be able to actually do it a little bit easier in your calculator in some of these cases where you're looking for rates and interest and time. Now, doubling an investment. Well, there's a thing called the rule of 72, and basically you can figure out how long an investment will take to double if you take 72 divided by whatever interest rate it is. So, I mean, approximately, if you take 72 divided by 10, you get 7.2%. And so you're basically looking at, okay, that would be the return, but if we use the rule of 72, it should double about every 10 years. So it's kind of a constant, I guess you might call it, mathematically anyway. Okay, here's a good summary of what we've been talking about: future value, present value, some of the meanings and symbols that are here in the chapter. And then the last thing I want to talk about is a spreadsheet. You can use Excel to compute these amounts. There are built-in formulas in Excel, but you have to be aware, like with a calculator, some things are a little bit quirky in Excel, and you may need to input certain things as negative in order to get the correct amount. So the future value, the present value, I don't remember for sure, but I think in each of these cases the payment amount needs to go in as a negative in order for it to calculate correctly. PV and FV are present value and future value. NPR is, or NPER is the number of periods, and rate is the discount or interest rate. So, I mean, that's what the different things mean. You can set up a spreadsheet and actually do these computations if you'd like. It's not hard to do, but getting used to it and figuring out the quirks that are in each of the formulas may take a little bit of time. But anyway, that's just a little bit about the Excel, the way you can use Excel. And in the chapter questions, you're going to look at questions and problems. Number one, you have simple interest versus compound interest. What is the difference? And they want you to compute the difference in money that you would have after 10 years if you were using simple versus compound. Number two here is to actually calculate future values. So you're going to go through this table and calculate the future value based on these factors. Number three, you're going to calculate present value. So this was future value. Here you're calculating the present value. So you have a future value and interest rate in years. Use those formulas in the book or your calculator to do that. And then with number four, they're asking you to find the missing interest rates. And this is really a matter of just taking the same formulas, putting the information in that you know, and then computing it so that you can actually arrive at what the interest rate should be. So I think that's really it for Chapter 4. I'm going to pause here and then we'll start with Chapter 5. Alright, with Chapter 5 we're looking at discounted cash flow valuation, and this is really looking at amounts that are paid out over a period of time, contracts, so on. They show pro athletes' contracts and how they're paid out over multiple years. When we're talking about future and present values of multiple cash flows, that's what we're talking about. We're talking about payments that are periodic that can either turn into larger amounts in the future, or we may need to evaluate what we should pay to receive those payments at the current time. So they show you here how that works. You're basically computing an amount, and you're showing it here growing in interest over the first 2 years. So what they're wanting you to do with this is you're considering not necessarily one lump sum payment, but a string of payments and what that value will grow to, or what is it worth now. So it's a matter of which perspective you're taking. Now the future value of these payments we're going to compute. If you look at this here, this is considered an annuity because there's a payment every period. In this case, it's paid at the end of the period rather than the beginning. So in this case, between 0 and 1, there's no calculated interest. But after year 1 and goes to year 2, there is. So the future value of this series of payments is $12,210.20. And we get that by just compounding the interest. And again, we use a similar situation to what we had in a lump sum, where we're counting the number of periods and we're looking at how long it's going to be invested. So here it's 4 periods, 3 periods, 2 periods, 1 period, and then this doesn't have any length of time being invested, so there's no interest on it, but we add all of these together to get the present or the future value of that amount of those payments. So we could have present value with multiple cash flows. We're basically in that case looking not at the future value, but what is it worth today. And in this case, we may have the opportunity to buy an investment that will tell us, okay, we'll pay you $1,000 each year for the next 5 years. What should I pay for that if the current rate is 6%? Well, given that, the amount I should pay is $4,212.37. And that would be an appropriate payment to receive those future promised payments. You notice that you could do that either way. You can do that here. They're showing the payments at the end of the year. The difference is that's the end of the year. Well, these are as well. So they're actually computing it backwards rather than the other way. From when you were actually looking at future value, you would have gone the other direction. A big question with present value is how much is it worth? If we pay for something now, what will it be worth in the future? So if we take a look at this, we're talking about this question, how much is it worth? You are offered an investment that will make 3 $5,000 payments. The first payment will occur in 4 years from today, the second in 5, the third one in 6. You can earn 11% interest. What is this investment worth today? Well, you do the calculations at 11%, and the present value for that will be $8,934.12. That's what you should pay for it. Now you can do this with your calculator as well, but remember, when you're getting to the present value part of this, that's going to be a negative amount because it's actually an outflow when you're actually paying for that particular investment. They show you here we can calculate the present value by discounting each year's salary. This is obviously not my salary. This is Colin Kaepernick's salary. So we can actually compute that and then discount it each year as we do, and then when we figure out what the actual value is of all those years of salary, we'll come up with the actual present value of that contract. You can do present value in a spreadsheet like this. It is very nice. They have a good Excel has a good function to do this with, but again, like I said before, it's a little quirky sometimes, and you need to know exactly how to input the amounts you need to put in to get these correct calculations out. If we look at level cash flows, we're looking at annuities and perpetuities. An annuity is a flat fixed rate that's being paid to you every year. It's an annual payment, or perhaps even more often than that. But the difference is the number of payments that are involved in periods. So when we're looking at annuities, we're looking at something that is paying out multiple times, not just one time, but maybe multiple times over the next several years. And so the present value factors will change. Now, like I said, when we're doing a lump sum, present value factors are almost always less than 1, but when we do annuities, not so, because it involves so many more payments and generally an extended, longer period of time that we're looking at. Annuities can be calculated using Excel. The formula is in Excel, and it's shown here. So future value is 0. Payment has a negative sign on it because the payment's an outflow. But you see there's a present value amount right here, $1243.43 for a 3 payment for $500 each payment contract. So I mean that's very similar to what we were talking about earlier. So if we want to find the payment, we're going to go about that a little bit differently, but we're basically following it's a mathematical formula, and we're solving for the unknown. So in this case, we have a present value of $100,000, an interest rate of 18%, and 5 years to make the payments. The payments are all equal, so we need to find the relevant annuity factor to solve for the unknown cash flow. So we do the computations here, and we wind up with 100,000 divided by 3.1272. That equals 31,977.78. So you'll make 5 payments of just under $32,000 each in order to have this $100,000 value at the end of that. Or no, not at the end of it. That's the present value. The future value will be greater than that. But that's the present value. That's what it's worth. Now, so annuity payments, here's another example. This is the problem that we're just talking about. You may want to find the number of payments. And again, this is going to be very similar to when you were looking at the interest rate. You're going to solve for the unknown factor in the computation, and you may actually need to adjust your approach. This is a good example of how to do it. Calculator hints are here, and they show you, again, like I said, these calculator hints are good, but you may have some variation on these with your calculator. I'm not sure what one they modeled this on, but you may be using a slightly different model or version. Let's see, I've got another calculator computation here. When we look at future value for annuities, again, this is going to be a growth factor, so the annuity will be a series of payments we're putting in, and we want to know what the future value factor is. We want to know what that will be, so it's a future value factor minus 1 divided by the rate, which is equal to 1 plus 1, or whatever the rate is, all raised to whatever power the number of periods there are. Computation of that is shown here. The annuity present value factor is equal to these computations, and you get 113.2832. So it's a 30-year, $2,000 annuity. That is a future value. So the future value of it is actually $2,000 times 113.2832, or $226,566.42. That's what the total value of that's going to be. All right. Now we have annuities due, and an annuity due is a payment that comes at the beginning of the period. So an annuity due is at the beginning of the period rather than the end of the period. The end of the period is an ordinary annuity. The beginning of the period is an annuity due. It's just a difference in the computation, because with an annuity due value, you have a different formula, a different calculation, a different table that you can use to calculate that. A perpetuity is something that goes on because the cash flows are perpetual. It doesn't end. because there's an infinite number of cash flows, we can't really compute the value by discounting each one, but we do have a formula here presented in 5.4 to calculate the present value of that. Basically, it's the cash, or the amount divided by the rate. It's cash flow divided by the rate. And they give you the example here. Here's the cash divided by the rate. You get 500 a year divided by 8%. So the perpetuity, the present value of that perpetuity is $62.50. All right. Here's a summary of annuities and perpetuity calculations. You can refer back to this. I would highly recommend that you go back and look at these tables periodically just to make sure you're on the right track. And then when we talk about comparing rates, we're going to talk about the effect of compounding periods. We have annual rates and compounding. We may have quarterly rates. We may have semi-annual rates, and so on. And that's what we're getting into here. When we talk about these, we're talking about individual savings accounts or accounts that are really compounding more frequently than others. And so if we're actually compounding 4 times a year, we have 4 periods in 1 year rather than 1 period. So it depends on how many times we compound in a year as to what we're actually looking at. A bank is offering 12%. Here's an example. 12% compounding quarterly. If you put 100 in an account, how much have you at the end of the year? And then they want to know what the actual they ask you to calculate the EAR. How much will you have on hand at the end of the 2 years? So really what the bank is doing is this. This is an important item to note. The annual rate is 12%, but you divide it by the number of periods that it's actually compounded. What it means is that if they're compounding it 4 times a year, that means you earn 3% a quarter. So you need to really think about it that way, because that's really more advantageous than a 12% a year, because they're compounding it every 3 months. So 3% every 3 months. So if you invest $100 for 4 periods at 3% per period, the future value then becomes calculated here, $112.55. So the EAR is 12.55%. That's the actual interest that you're earning on that. So you would have at the end of the 1 year, $112.55. What we need to do with this is when we have a case where there's an interest rate stated on an annual basis, and the bank or the investment tool compounds interest more frequently, like quarterly, semi-monthly, or semi-annually, whatever it is, or monthly even, we need to divide that interest rate by however many periods in that year there are that the bank is compounding the rate. In this case, it was 4. There may be cases where it's 6, or where it may be 12, or it just depends. So just to be aware of that, how that impacts the computation. So what we're actually doing here when we're quoting a rate is we're converting a quoted rate into the actual rate, the effective annual rate that we're actually going to get. In other words, they may quote us a rate at, in this case, 18%, and but we're going to have monthly compounding. So if we're going to have monthly compounding, the rate's going to actually be compounded at 1.5% per month rather than 18% a year. So we're actually going to be computing the compounding more frequently, and it's going to be to our advantage to do that. So if we're going to solve for that, the effective annual rate, if we look at this after we say, okay, we're going to compound this, the effective annual rate is 18%. The actual stated rate would be more like 16.6%. If you don't know what that rate will be. Annual percentage rates are basically how most people state these. And that really is important when you're looking at loans and things like that, looking at what rate you're paying. So if you have an APR of 18% with monthly payments, you really like taking 18% divided by 12, or 1.5% per month. The effective annual rate then from the 18% that we started with is 19.56%. That's the rate we're actually paying, which is higher than what is stated. So, for example, with this effective annual rate, what you're looking at, this is a check into cash. You can write a check for $352.94 dated 14 days in the future. They're going to give you $300 today. So what are the APR and effective annual interest rate of this arrangement? First, if you find the interest rate, you can do that through the future value computation, and you get a rate of 17.65%. Doesn't seem too bad until you remember that rate is only for 14 days. So then the annual percentage rate of the loan is actually 460.07%, and the effective annual rate for the loan, oh my goodness, is actually 6,183.89%. That's a humongous rate. That's incredible. So that's an example of the effective annual rate, or effective interest rate. So really with loan types and loan amortization, which is what comes next, we can talk about different approaches to that. When we're talking about a loan where you have a discount loan, a pure discount loan, is basically you're receiving the money today and repaying a single lump sum at some time in the future. So you may have a pure discount loan, for example, require the borrower to repay $1.1 in 1 year for every dollar they borrowed today. It's not hard to value that kind of a loan. It's pretty straightforward. But if we're looking at interest-only loans, where we're calling for the borrower to pay interest each period and then repay the entire balance at the end of the loan or some point in the future, that's like a balloon payment. They're called interest-only loans. And if there's just one period, a pure discount loan and an interest-only loan are the same thing, but you may have more than one period. An amortized loan is what you normally see. This is going to be where you have a payment split between interest and principal, and you actually compute it out over a period of time. So in this case, you have a number of periods. Let's say you're borrowing $5,000, and it's going to be for 5 years. Your payment in the first year of $1,450, you're paying $450 in interest. The principal is $1,000. The ending balance is this, and then you go through, and through the next several payments, you're liquidating down that balance, and you'll see the interest paid is reduced each time you make a payment. With these amortization schedules, what they are is they're a good way for you to figure out just what you're going to have to pay and how you're going to pay it, and how much will go to interest, and so on. So here, this is basically taking the same amount and saying, okay, I'll pay a fixed amount each month or each year. How much will that reduce my balance? What will my ending balance be? If I make 5 equal payments of $1,285.46, it'll be paid off at the end of 5 years. Basically, this kind of a schedule shows a decline in the balance to zero based on computation of interest in each period, and you show that split between payment for interest and payment on principal. This is an example found on the web. The nice thing about Excel is you can do a loan amortization very nicely in Excel. It's not hard to do. The table you saw just a moment ago as an example is very easy to replicate in Excel. And the good thing about Excel, the one thing that they're not going to, I don't know if they're going to talk about here in the book or not, but you can reference the formulas two different locations, and basically here, example, they have the formulas referenced. They're showing you what the formulas are. If you use formulas in this table, you can change the dollar amount, and you can see what the amounts are going to be in each different case. So these are references, and this is where you do the input. So you have an input range here, and if you change the loan amount, the interest rate, or the loan term, or even the loan payment, you're going, well, the loan payment's calculated, but if you change any of these, you're going to actually wind up changing the whole table, and it will flow through as long as you have it set up the way they show it here, which is why I think Excel has an advantage over manually calculating it, because you can actually set up a schedule that works and then change it based on the amount that you want to compute for. So with Chapter 5, we've talked about a lot of those, the annuities, series of cash flows, the present value, future value of those, and payments. I want to get to the problems they're asking you to do here. In number 1 in Chapter 5 is they want you to, they have this Ulyss company has identified an investment project with the following cash flows. If the discount rate's 10%, what is the present value of the cash flows? What is the present value at 18% or 24%? And here you're just using the present value of a series of cash flows, and you're going to calculate those based on these different cash flows. So you have different amounts each year, but you'll have one total value in that computation for the cash flow. Number 2, present value and multiple cash flows. This is present value, multiple cash flows as well. But here it says investment X offers to pay you $3,400 for 9 years, whereas investment Y says $5,200 per year for 5 years. Which is of the cash flow streams has a higher present value if the discount rate is at 6%? What if the discount rate is at 22%? Which one has a higher present value? So you want to look at those and calculate those. Future value, multiple cash flows. You've identified an investment project here on number 3, and you have a discount rate of 8%. What's the future value of these cash flows in year 4? What is the future value at an interest rate of 11% or 24%? You have the cash flows. You just need to calculate those future values. Then skip number 4, go to number 5, and here for each of these annuities calculate the annual cash flow. And again, you have the present value, the years, the interest rate, and you're just going to use those annuity calculations that we talked about earlier to figure out what the annual cash flow for each one of them is going to be. And you can do that from the present value, the years it's invested, and the interest rate. So that's really all of the assignment for Chapter 5. We'll take a break and come back to Chapter 6.